Hi, in the last session, we have analyzed our design graphically. We have used RTL Viewer for high level structural design and Technology Map Viewer for detailed structural design. We have navigated through different elements in our design too. Now, this is the time to review some of the important reports to analyze your design in little more details. And by doing this, you will know that how Quartus Prime take the decisions to configure your designs. And you will also need to learn that how you can override Quartus Prime configuration based on your specific design requirements. So we are going to start with Fitter reports. And these reports will tell you about the resources utilization of different elements of your FPGA that was occupied by your design. For example, how many CLBs are used? How many registers has been used? Are these logical registers or input-output registers? How many memory elements has been used? How many PLLs are used? How many input and output ports are used? So these reports contains a lot of informations about your design and your FPGA device. These reports also tell you about that how much resources in FPGA are remaining too, so that you can know that how complex design you can still make on your FPGA device. We will also discuss global netlist, and you will learn that what signals or ports should be promoted to the global netlist in your design or should be treated as a fast signal or not. Okay, so that is enough introduction. Let's jump to the Quartus Prime software. But before this, one important note that all of these Fitter reports you will be able to see only after a full compilation run. Now, let's move to the Quartus Prime software now. Okay, so after the netlist viewer and the RTL viewer, we will look into the Fitter report. And for this, we will go to this compilation report section. And now here you will see this Fitter report section. So once we expand this, you will see a lot of reports here in this category. Now remember that this Fitter report will only be published after your full compilation. So once your compilation report is fully completed, then you can come here to review these Fitter reports. All right. So first important report is this summary. So it will give you a quick brief about the resource utilization, your input output port utilization, your FPGA device, your top level module, etc. So for example, this is your top level module that is named as IP test. You have selected this Cyclone 4 family device and the device name is this one. Now you can see that the total logical elements that has been used by this program or this IP test module, these are 9 in total, and your FPGA device means this device has total 6272 total logical elements. So that's come up with the less than 1% resources. And that can give you confidence that how complex you can design your project for this specific FPGA device. So this project is really very small and that is only consuming 9 elements from this 6272 total elements. All right. Now next is total registers. So your module is using 6 registers for this project. Next is total pins. So your FPGA device has total number of 92 input output pins, and out of this 92, your project is using total 8 input output ports, and that counts 9% of total. You can also see about the memory elements or the memory utilization. So this 276,480 is your total available memory bits, and we have not used any single bits for this memory elements. And remember that this is different from this total registers. So in this module, we are using 6 registers, but we are not using any memory bits. These memory bits mainly comes when you are using memory IPs in your module or the RAM elements or the ROM elements inside your module. All right. So we have not used any such elements in this program. So that is why this is 0 here. We do also have the multipliers inside this FPGA device. So this FPGA supports 39-bit multiplier. And again, we are not using any element from it. All right. Now the next is total PLLs. So this FPGA device supports 2 PLLs. And out of this, we have already used 1 PLL in this project. Means you can use 1 extra PLL in this program. So this is the quick overview of the resource utilization of your FPGA device. Now coming to the next report, so this is settings, and here you can see all the settings that has been used by the Quartus Prime software for this project design. Alright. And the important thing is that these two columns that display the default values and also your configured values, so you can easily navigate if any of the values are different from the default value. So you can go through them if you really wanted to read them. But for this project, we have not changed much of the configurations. So maximum settings are same as their default values. All right. Now, next important report is this resource selection. So if you expand this, then you will see multiple reports listed here. So the first one is resource usage summary. So this report is a little drill down version from the summary report that we have reviewed. So you can see that the total number of logical elements are 9 out of 6272 total elements. And these 9 elements are bifurcated into these 3 type of elements, right? So you can see that the combination block with no registers, so these are used as 3 number of total counts. Next, 2 elements are only registers. These are not derived by any lookup tables. And rest of the 4 elements are the combination elements with registers. Now this is important to understand that CLBs are the basic elements inside your FPGA device. So for example, this device has total 6272 CLBs inside it, and these CLBs are derived from a kind of lookup tables. Means these 3 elements are derived from the lookup tables without any registers. These 2 elements are only registers and they are not derived from any lookup table. And these 4 elements are the combination of the lookup tables with registers. Alright. Now, if you are not aware about the CLBs and the lookup tables and how these works inside the FPGA device, then please watch my FPGA basics section. That is really important to understand that how the CLBs and lookup tables works for an FPGA and how Quartus Prime software configures them for any desired requirements. Now coming to this next section. So now this is telling that there are 3 elements that has been used as in 4 input functions, and rest of the 4 elements are used as in less than 2 input functions, and 2 are registers only. So you can see these are 2 are registers only. All right. Now if you go a little down, then you will see this register section. And if you remember from the netlist viewer, then we have seen total 6 registers there, right? So 3 registers was for driving the LED outputs and 3 more registers for driving the current state of our finite state machine, right? So in total, we have used total 6 registers for this project, all right? So you can see that there are total 6 dedicated logical registers that has been used out of total 6272 registers, and that contributes less than 1% of resources. Now, this is really important to understand the input-output registers. So these input-output registers are important because if your registers are placed far from the input-output ports of your FPGA device, then the signal will take more time to reach to the input-output registers, and that will add up the timing delays while reaching to these registers. Although this time will be very small, and this is acceptable if you are working on some slow speed devices, like here in this case we are designing. But if you are really working on some fast device that is operating on some really a very high speed frequency, then we will prefer to use these input output registers to drive our output more quickly. So if you wanted to get our output little faster, then we can use these input output registers which are placed near to the input output ports of your FPGA device. Alright. But for this project, we are not using any input output registers. So all are dedicated logical registers here. Alright. Next is input output pins. So you can see that we have used 8 input output pins out of total 92 pins. Alright. Next is the memory elements or the memory blocks. So you can see that we have total 30 number of memory blocks here, and that can store this number of bits. So you can see this is total block memory bits, and these are grouped inside this 30 elements or 30 memory elements. Next we have these 9-bit multipliers, and we have not used any one in this project. So the utilization is 0%. We have used 1 PLL out of 2. So that contributes the 50% utilization of PLLs. Next we have these global signals. So we have 2 global signals in this project. We will come to this little later. Next we have this global clock. So we have 10 in total, and we have occupied 2 number of them. So that contributes 20% of resources. You can also look at this maximum fan out. So that is 7 here. This means that one signal is driving how many elements are in the FPGA. So for this project, we would be having one signal that is derived 7 different elements. And you can look the netlist viewer to map that signal. Okay. And next is total fan out. So that is 60. That is okay, but maximum fan out is really important to understand. Now coming to the next report, and this is next is input pins. So you can see that all the input pins are listed here. So we have clock, reset, and 3 switch inputs. And these input ports are connected to these pins of FPGA. Next column is input output bank. We have already explained these banks in the previous session, so you can go and look for them if needed. Next is combinational fan out. So you know that clock has the one combinational fan out because that is only connected to the input of our PLL, and all the other elements are derived from the output of that PLL. So this clock has the fan out of 1. And same you can see for the reset. So that is connected to the 7 elements, or you can say that reset is driving 7 different elements inside our project. You can also map it into the netlist viewer. All right. Registered fan out, we have 0. Now, if I go to little right hand side, then you will see this global nets. We will talk about this global nets little later. Next, we have these input output standards. So we have selected these values for our input output ports. So for our FPGA board, this is 3.3 volt LT, LB, TTL. All right. So same way you can check for the output reports or the output pins. So these 3 are our LED outputs, and these are connected to these FPGA pins 85, 86, and 87. Next column is the input output bank. Input output standards 3.3 volt TTL. So you can go and look into them one by one, but I'm not going in detail much here. Now the next report is PLL summary. So that will be generated if you are going to use any PLL inside your project. So we have used one PLL in this. So that is a summary of it, that what is the input frequency, what is the output frequency, what will be the VCO frequency. So there are many informations listed here. You can just go through them if needed. Next is PLL uses. So we have used this clock PLL inside this project. So that is having the output frequency of 25 megahertz, and that will use the division factor of 2. The output clock will be clock 0. Duty cycle will be 50-50. So you can quickly review them if these are matching with your requirements or not. Now the next important report is resource utilization by entity. So this report is really important when you are using many modules inside your top level module and you really have a big hierarchy of your designs. So for example, if you select the hierarchy view from here, and this is our top level module, and if you expand this, then you can see that we have used this PLL as a component here, right? So you can see the same thing here as well. So this is our top level module, and inside this we have used this component as PLL. Okay. Now, if you look at this PLL, then all the resources are 0 here because they are not consuming any of the resource from the FPGA CLBs, because we are using a dedicated PLL for this clock PLL component. All right. But for this IP test module, which is actually having a finite state machines, we are consuming FPGA resources, or we can say that we are consuming the CLB resources from our FPGA device. So for example, we are using 9 logical elements. We have 6 dedicated logical registers. We are not using any input output registers. We have already seen them in the previous reports as well. So this report is a bifurcation if you are using many modules inside your project. So you can see that how much resources are consumed by the each module. So this is really important view if you are working on really complex design. Now the next report will be control signals, and this is really important to understand. So generally all the clock signals and reset signals are treated as in control signals. And this report tells you that what are the signals which are driving multiple elements inside your FPGA. So in this case here, we can see that we have 3 signals or 3 ports. These are treated as a control signals by the Quartus Prime software. And Quartus Prime automatically identified them for your projects. So Quartus Prime has identified 3 different signals which should act as in control signals for this project. And these are clock and reset, and 1 clock output from our clock PLL. Alright. So these are the location of input output ports or any other signals that has been used. So clock is connected to pin number 23, reset is connected to pin number 25, and the 25 megahertz clock output is connected at the PLL1. All right. Now, if you look at this global column, so that is telling that if the port or signal is a global net or not. So you can see that Quartus Prime has selected this PLL output, that is a 25 megahertz clock, as in global net. Also, the reset port is acted as in global net. But our main clock frequency, that is our port frequency, that is not treated as a global net. Now this is decided based on this fan out numbers. So you can see that this clock input has the fan out value is 1 because this clock input is directly connected to the input port of our PLL, and then we will be getting a 25 megahertz of clock signal, and that 25 megahertz of clock frequency was driving all the other elements inside the FPGA, right? So that is why this clock input is treated as not a global net, okay? But this PLL output, which is again a clock frequency, and that is driving 6 different elements inside our FPGA. So that is why that is treated as a global net. All right. So that is really important to understand that what should be your global nets and what should not be a global net. In case you are thinking that some of your signals are driving multiple elements of your FPGA, but Quartus Prime did not consider that as a global net, then in that case, you have to configure that signal and promote that to the global net. Okay. And don't worry, I will tell you that how you can promote any normal signal to a global net signal. Okay. Now, if we go little right, let's see what extra details we have. Now we will jump to the next report, and that is global and other fast signals. And this report is actually a subversion of this control signals. So you can see that we have these two signals. These are identified as the global net. So these two global nets are listed here. So we have this 25 megahertz of clock, that is a PLL output, and we have reset. All right. So you can see that this Fitter report has a lot of informations which you should review for almost all of your projects. And they will give you a good overview about the resource utilizations, your signal specifications, input output port specifications, and many more things. And now we will tell you that how you can change the configurations if you wanted to override the Quartus decisions on your projects. Like how you can promote the normal netlist to a global netlist, or how you can promote the normal registers or the dedicated registers to the input output registers. Okay, so that was some of the important Fitter reports that I think you should review for all of your projects. These gives a lot of insights about your designs and your FPGA device. Next, you will learn that how you can modify Quartus configuration and promote any normal signal into a global netlist signal, and also how you can change any dedicated logical registers into the input output register. So stay tuned for the updates, and I will see you in the next session.